Good evening, young algebra students. So today we are beginning a new chapter, and this chapter is all about functions and comparing two quantities to each other. And today we're just doing kind of an introduction of that by using graphs. So today what I would like for you to be able to do by the end of the lesson is to read and describe information represented in graphs of two quantities, and I'd like for you to be able to create your own graphs when given a word problem representing two quantities. So first of all, you've seen graphs before, you have been exposed to them, but what graphs are useful for? Why do we use them? Well, they're useful to organize and present data. So there are certain strategies to different types of graphs, and they let us visualize and understand different pieces of information more clearly. So that's kind of the benefit of graphs. And what we would like to be able to do is look at a graph and really understand what it's depicting. So let's look at this first example. It's called Analyzing a Graph. And let's see if we can kind of describe what's going on in this image. So it says, Lena makes home deliveries of groceries for a supermarket. Her only stops after she leaves the supermarket are at traffic lights and the homes where she makes the deliveries. The graph shows her distance from the store on her first trip for the day. What are the variables? Describe how the variables are related at various points on the graph. So basically what we have going on is Lena has groceries in the back of her car. She's going to take them to different places, and then when she drops everything off, she's going to come back to the store to likely get another pickup and then go deliver more. So what are my two variables? To locate your variables, you can oftentimes look at the labels on the axes to know that. So my variables are time and distance, but I'm going to be a little more specific about distance. I'm going to say distance from the store, or supermarket is what they call it, but same difference. So these are the two quantities that I'm comparing, and now we're just going to pick a couple points on the graph and kind of describe what's going on. So right here at the very beginning of our graph, because we're reading this from left to right, at this very first point, I'm going to label it point A just so we know what exactly I'm talking about. At point A, no time has passed and she has not left the store. Notice time has not progressed at all and the distance is at 0, so she has not left the store. So no time has passed and Lena is still at the store. All right, let's just pick another random spot, and let's say that is right here, B. So notice time has progressed. Time keeps progressing, but she's not getting further away. She's getting further away. Time keeps progressing, and then she's not getting further away anymore. So it looks like at point B, one of two things have happened. Either she has stopped at a house to deliver groceries, so she's not really getting any further away from work because she's remaining there. Or she's at a stoplight. We don't know, but we do know that she remains at a constant distance away from work. So B is going to be Lena has stopped and remains a constant distance from work for a certain amount of time. And let's see here. Let's choose this point right here to this point right here. So I'm going to say from C to D. So C, Lena has clearly made her last stop. She's not continuing going further away from the store. So C is Lena has made her last stop. And D is, oh, she's beginning. The D is right at the beginning of where she's going to start returning back to the supermarket. So Lena begins returning back to the supermarket. And I think that's plenty for this. We just needed to pick a couple points and describe what was going on, and I think that's a pretty good description. We're going to do the same thing for problem B. It says the graph shows Jesse's cell phone bill for the month of June. What are the variables? Describe how the variables are related at various points on the graph. Once again, we're going to look at the axes to know what type of variables we're working with. So I'm going to say variables. And let's see here, we have minutes of calls. Now, we don't really have this a whole bunch anymore, but I mean, you can get a prepaid phone. And basically, you are allowed a certain time limit for your cell phone calls. And then when you exceed that, then either your phone gets turned off or your bill goes up or something like that. And then we have cost as well. So I'm going to say minutes of calls and cost. Those are my two variables. Now notice how the minutes of calls is increasing. Maybe they went from 5 minutes to 10 minutes to an hour to 2 hours to 3 hours, and then all of a sudden the cost starts going up. So what this is letting us know is the cost is consistent until a certain threshold is met, and once Jesse reaches that maximum, then his bill goes up. So we're going to say that Jesse's bill is constant for a certain amount of time. But once this point right here is reached, once he reaches that, his bill increases. They start charging him more. So then once Jesse reaches his minute maximum, his bill increases. And it looks like possibly per minute or maybe per hour. I'm not sure because we don't really have units here, but you can make some decent theories about that. Moving on to example C, I know the ink is very difficult to see, so what I'm going to try to do is to kind of take this eraser a little bit and get rid of some of that ink to hopefully make this a little more visible for you guys. That's a little bit better, and I will just put this highlighter on it. That might help. I have no idea. The ink is a little too dark. But all we're going to do here, it says the graph relates the height of the water to the volume of the water in each container. So we've got 3 containers right here and 3 graphs right here. And it says which graph goes with each container. I'm going to go ahead and label these real fast just so we don't have to worry about what we're talking about with which is which. So I'm going to say graph A, graph B, and graph C, and then container 1, container 2, and container 3, just like that. Now what I want you to notice first off, this graph B and graph C, are both straight lines, while graph A has a curve in it. We might be able to relate that to the shapes of the beakers that this water is in as well. Notice how this is straight up and down. This cylinder is straight up and down, but this cylinder has a funnel on it. So I'm going to go ahead and say that A goes with 3. Because I can clearly see that the height and the volume does not increase consistently, and that would be correspondent with container 3. Now let's look at graph B. The height is growing very, very slowly. The height doesn't get very tall, while the volume grows kind of quickly. Well, just looking at our other two options, beaker A has quite a short height, so that would be the most logical one to match with that. So I'm going to say B with 1. And then we don't have many options left, so I'm going to say C with 2. Kind of the process of elimination there. We are going to do the same thing, or at least something very similar, on this back side. It says matching a table and a graph. So here it says the table shows the amount of sunscreen left in a can based on the number of times the sunscreen has been used. Which graph could represent the data shown in the table? So we have used the sunscreen 3 times, 0 times, 1 times, 2 times, and 3 times. If I don't use any sunscreen at all, then there are still 5 ounces of sunscreen left. But when I use it 3 times, there's still quite a bit. There's 4.4 ounces left. So looking at our graph options, right off the bat, we know that A is not a possibility. So it is not A because if you notice this point right here, this guy, it says that after 3 uses, there's 0 ounces left. That's what that's saying right there. Well, we know that's not true. There's actually 4.4. So not A because it goes to 0 ounces. Let's look at graph B. Graph B, notice how it curves and it drops off rather quickly. Well, let's look at our points. I have 5, 4.8, 4.6, and 4.4. Those are rather small increments. I'm only moving by 0.2 each time. So graph B drops off really fast, and that's not going to be very realistic for this problem. So it's not B because it drops off too quickly. So now C is our last choice, and so I'm just going to say it has to be C. And notice how C gradually goes down. As your uses go up, the amount of sunscreen in the container goes down, but slowly. All right, the last thing that we're going to do, we are going to draw 2 graphs. And it says, suppose you start to, well, the first one, problem A, it says, suppose you start to swing yourself on a playground swing. You move back and forth and swing higher in the air. Then you suddenly swing to a stop. What sketch of a graph could represent how your height from the ground might change over time? Label each section. Now, I'm not going to go into too extensive of detail because I know swinging is going to be quite, it has a lot of fluctuation in it based off of the variables that we have. But remember, let's go ahead and locate what our variables are. It says, what sketch of a graph could represent how your height from the ground might change over time? So these are my variables, height from ground and time. And time is oftentimes the independent variable. So I'm going to go ahead and put time right here. And then I'm going to say height from ground right there. Okay. Now, I want to put a couple more kind of tick marks in this because I want to be at least pretty detailed, and I'm going to be relatively, consistent as best as I can. So I'm going to say the time is going to be in seconds because as you're swinging, you're working kind of like a pendulum, and you're swinging and you're getting high, and then you're getting low, and then you're getting high rather quickly, and then low, and then back high because of the motion that a swing goes in. So I'm going to say height from ground is going to be in feet. And as we know, so let's say that time is at 0. Well, are we 0 feet in the air? That doesn't make any sense because swings are not completely on the ground. They're usually a couple feet in the air, like those, so you can sit on them. So I'm going to say at 0 time, we're about 3 feet in the air. This is just something I'm making up. There can be many graphs that represent the same concept that do look a bit different. Okay, now I'm going to start to swing. So I'm going to go up. But here's the thing. Because you're on a swing, because you go up, you must come down. And then you go up, and then you must come down again. So right now, let's say that we are on a swing. We're swinging up, and then we come back down, and then we swing to the back. And then we come back down, and we swing to the front again. And we keep doing that until we reach, I don't know, a maximum level. We can't swing any higher, and then we start slowing down back and forth until we stop again. So we swung forward, and now we're swinging back down, but we're not going to go lower than 3 feet because that's as far as like the swing chain or swing rope goes. And then we're swinging backwards, but we're going a little bit higher again. And then we go back down. And then we go a little bit higher again. And then we come straight back down because we're constantly going back to this low point because remember that swing is going back and forth, high, low, high, low, high, low, forwards and backwards. So then we go even further. We're starting to really gain some momentum. So we're going to be this high. And then all of a sudden, let's say we get scared. So, we're coming. We're going to try to start slowing down. We're going to slow down as fast as we can. Maybe we drag our feet in the dirt a little bit until we come to a stop. So the way this is going to look as we progress through time is like so. Because remember, you're consistently returning back to the lower part of your swing, while this up here represents the highest swing that you, that you swing. So I'm going to say this is highest swing and coming to a stop. All right. We have one more graph that we need to do, and it says Emma dives off a cliff into a lake. So I think she's like going swimming or something like that. And it says the edge of the cliff is 12 meters above the water, and she hits the water 5 meters from the edge of the cliff. Construct a graph below that shows the relationship between her height above the water and her distance in meters from the edge of the cliff. So what we should first do, because this is a little wordy, we should go ahead and draw ourselves an image. So let's say that this is our rocky cliff. I don't know, maybe there's a tree up here just so we can kind of get some. And then here is Emma. She's about to dive off, and she's going to go into this picturesque lake down here. So maybe she's already got some friends who are splashing around or something. We got a fish in there. So she's going to go jump into this lake. We know right now it says the edge of the cliff is 12 meters above the water. So we know we've got 12 meters. And eventually when she jumps into the water, she's going to be 5 meters away from the edge of the cliff. So let's label our axes now that we have a little bit of a better idea about what's going on. So we have distance from cliff, and we have height from water. Okay. If her distance from the cliff is 0, that means she is currently standing on the cliff. So she's at 0, but how high above the water is she? She is 12 meters. So I'm going to count by 2, 2, 4, 6, 8, 10, 12. So right here, she is 12 meters above the water, but she is 0 away from the edge of the cliff. Then she's going to jump and kind of take this path and go down there. Now here's the thing. We can't say, oh, she's 5 meters away from the cliff, because she's not. She's actually this diagonal distance away from the edge of the cliff. So we're going to do this little thing called the Pythagorean theorem real fast. You've more than likely heard of this. It's a squared plus b squared equals c squared. So we're just going to say 5 squared plus 12 squared is equal to c squared. 25 plus 144 is equal to c squared. And I'm going to get 169 is equal to c squared. Square root c is equal to 13. So that was just a quick little side calculation so I can figure out this distance right here. Here, I'll highlight it in yellow for you. I'm trying to figure out this distance because when she lands in the water down here, she's not 5 meters away from the edge of the cliff. She is this distance away from the cliff, but I used a triangle to kind of figure that out. So we now know that when she is 0 away from the water, or 0 meters away from the water, which is going to be down here, she's going to be 13 meters away from the edge of the cliff. So I'm going to go 2, 4, 6, 8, 10, 12, and then 13 will be in the middle right here. And then I just connect the 2 dots. And there's my graph. So this graph is kind of illustrating, oh, as her distance from the cliff gets further away, her height from the water gets closer. Well, that's everything that I have for you today. I hope that this is making sense, and we'll be practicing more with graphs tomorrow. Have a good night.